alkenes can do a variety of different reactions. Most of these reactions are going to fall underneath the mechanistic classification as electrophilic addition, or EA is the informal abbreviation for that. In yesterday's lesson, I talked about both catalytic hydrogenation and the electrophilic addition of a halogenic acid to an alkene. In this lesson, we're going to look at two reactions, but both of them have the same general feature. They're both going to convert an alkene to an alcohol. Those are the reactions we're going to look at today. The first one puts the alcohol at the Markovnikov position, and the second one puts the alcohol at the anti-Markovnikov position via syn addition. And we'll talk about what all of this means when we get to that particular example. The first mechanism that shows up in today's lesson is the reaction of propylene with 50% sulfuric acid and water. Propylene is the common name for propene. That's a 3-carbon alkene. We don't bother to specify the 1 position because wherever the alkene starts is the 1 position. And we're going to react this with sulfuric acid and water. And what I have shown here in black is the defining feature of electrophilic addition. As I tried to explain in the last lesson, what we see over and over and over again with electrophilic addition is the pi bond hinges out to go pick up something and leaves behind a carbocation. So this nature of hinging out to produce a carbocation is the thing that makes this electrophilic addition. Now the thing that it's hinging out is the same general class of molecules that we looked at yesterday, those being strong acids. Sulfuric acid, when mixed with water, sulfuric acid is by definition a strong acid, so it reacts with water to form the hydronium ion. And while hydronium is not itself defined as a strong acid, it's the strongest of the weak acid and strong enough to pull the pi bond electrons out and form that carbocation. The carbocation has to choose between either side of the double bond. In this mechanism, the carbocation ends up on the secondary position and not on the primary position because the secondary position is more stable. The rest of the features of this mechanism are exactly what you expect to occur when you have an aqueous solution. That's a solution with a lot of water, which is what happens when you have 50% water, and a carbocation. Water jumps on the carbocation, another water molecule will deprotonate the alkyl oxonium ion, and we end up with an alcohol. From start to finish, this is referred to as the hydration of an alkene. The mechanism is electrophilic addition. And you can see where the mechanism is defined as electrophilic addition because the pi bond reaches out and leaves behind a carbocation. The final alcohol product ends up capturing the carbocation, and the carbocation will show up at the more substituted position of the alkene. It would be the nicest thing in the world if organic chemists would call that carbon the more substituted position and not make up another term, but we are ruled by tradition, and that carbocation is showing up at the Markovnikov position. And so when you look at your product, the alcohol is a secondary alcohol that we produce, and therefore the alcohol showed up on the more substituted position of the alkene, and this therefore is the Markovnikov alcohol. There will be some very limited amount of primary carbocation that forms. We do not expect that to be even a minor product that we would look for, but given trillions upon trillions of molecules that are reacting inside of a 5 ml reaction container, some of the pi bonds are going to swivel out the wrong direction and produce a carbocation at the primary position. Then that primary carbocation, we'd expect it to rapidly shift, but some small percentage of those very, very small percentages of primary carbocations won't shift, and ultimately you will end up with some product where the alcohol is out here on the primary position. We would refer to that as an anti-Markovnikov alcohol. That would be the minor product. This reaction, the hydration of an alkene using aqueous sulfuric acid, will produce the Markovnikov alcohol. The energy diagram for this reaction would have 1, 2, 3 distinct humps. The first step is the rate determining step because that's where you form the carbocation. So that's what I'm showing, crawling up the energy hill and getting to this secondary carbocation would form right there. When the water captures that carbocation, we see a large drop in energy, and then a little acid-base chemistry at the end that gives us a more stable product. So this is the energy diagram for the reaction. What would happen if we used concentrated sulfuric acid instead? And so notice in black I still have the central features of electrophilic addition. The pi bond reaches out to pick up an electrophile and forms a carbocation. This, again, is the key feature that we're going to see over and over again in this chapter. All we're really going to do is just change the electrophile. So if we have concentrated sulfuric acid, there isn't water present. There will always be some water, but ignoring that little detail, if it's concentrated, the assumption is that it's a trivial amount of water, so the sulfuric acid will be the thing that directly protonates your alkene. And then in the absence of water, the only thing that can really stick to your carbocation would be this hydrogen sulfate conjugate base of your original acid. This ends up producing a class of molecules referred to as alkyl sulfonates. These are interesting as byproducts for additional chemistry, but I really haven't seen very many examples where we encounter a lot of alkyl sulfonates. So as a curiosity, if you used concentrated sulfuric acid, this is what we'd form in this reaction. And maybe we'll come back and talk about some things that this molecule can do in the future, but it's really not that important of a molecule that we produce. You can make it this way, but it's not a big deal. The next question is, what happens if I added sodium bromide into that original solution? So this is not a modification of part B, but rather a modification of part A. And so we need to think about this from the perspective. We have a 50% solution of sulfuric acid with water, and we also sprinkled in some sodium bromide crystals. Those will immediately dissolve in water. The sodium will be carted off as a spectator ion, and that means you have bromide ions floating along in solution. The bromides would be unreactive towards the alkene, so we'd still expect that same first step. So I'm going to go back down to the mechanism. So this first step is the characteristic electrophilic addition step in an acid. The alkene swivels out to grab a hydrogen off of a strong acid and produces a secondary carbocation. If sodium bromide is present, now water has competition for that carbocation. So when the sodium bromide wasn't present and we had a 50% solution, we brought the water in. That was part A. In this part C, we're assuming that there's enough sodium bromide. The bromide can outcompete the water and comes in and catches this carbocation. This gives us the exact same product that we got yesterday when we added straight hydrobromic acid. So you might ask, why would anybody add sodium bromide and sulfuric acid when they could just add hydrobromic acid? And the short answer is hydrobromic acid is a difficult reagent to work with in the laboratory. Sulfuric acid is cheaper, it's more abundant, we produce a ton of it every year, and so you can just use the sulfuric acid to catalyze the formation of the carbocation, and then put a bunch of sodium bromide in there, and this is a mimic of hydrobromic acid. Sodium bromide plus sulfuric acid behaves as if it were hydrobromic acid. The final question related to this hydration of an alkene, which is, so if you think about kind of the sequence of questions here I have kind of the standard. We're going to use 50% sulfuric acid in water, and this is what we expect to occur. Notice you do form a carbocation, so if a shift is possible, then that would introduce some complexity. But pretty much you get these three steps right here where the alkene picks up a hydrogen, the water jumps on the carbocation, something deprotonates the water, we end up with an alcohol. And then kind of some what-if questions. What if we don't add water? Well, then we're going to get some alkyl sulfates. What if we contaminate our water with sodium bromide? Well, then you'll get an alkyl halide. And now what if I use a different alkene? So this question asks about 2-methylpropene, which is down here on the bottom, versus propene, which is the systematic name for this compound up here on top, and it's still the same first step of the mechanism. And since the question is specifically asking me about the rate of the reaction, the only step I care about is that rate determining step. So in the rate determining step, I am making a carbocation. 2-methylpropene is going to produce a tertiary carbocation, whereas regular old propene will just produce a secondary carbocation. And so this tertiary carbocation right here is more stable and therefore will form faster. So what would happen to the rate? Well, 2-methylpropene would react faster because the rate determining step involves the formation of a carbocation. 2-methylpropene produces a tertiary carbocation, which is more stable and forms faster, whereas propene involves the slower formation of a secondary carbocation, hopefully reminding you of the fact that tertiary carbocations are easier to make, faster to form than secondary carbocations in the reactions that we've seen. This next question is a reminder of what happens when you take an alcohol and react it with a large acid. You should be able to show this mechanism without me walking you through it. This is a question taken right off of the advanced DUI table. For your own sake, you should pause the video, see if you can come up with the mechanism on your own, and then come back to this video when you're ready to look at the answer. To answer this question, what I want to show you is we've already kind of looked at this process. The very first question that I looked at was the reaction of propylene, the common name, also known as propene, the systematic name, with aqueous sulfuric acid to form 2-propanol. The question that I want you to think about right now is the reverse of that. 2-propanol with diluted sulfuric acid, right here, 2-propanol with diluted sulfuric acid to form the alkene. Okay? If you looked hopefully at the DUI table or remembered that secondary alcohols react with sulfuric acid via an E1 elimination pathway to produce an alkene. And so this reaction in question number 2 is simply the reverse of the reaction in question number 1. And this illustrates this concept that's referred to as the principle of microscopic reversibility. And the principle of microscopic reversibility tells us that for a reversible process, so remember in the first reaction we went from left to right. Now what we're doing is going from right to left. So I'm going to go ahead and change the order of the reaction by flipping everything horizontally. Let's see if I get this to work. It's going to be a little messy at first. Just the lone pair. And so what I just did, let's color everything black now because we're no longer looking at that previous question. So this right here represents the reaction of 2-propanol to form this alkene. The principle of microscopic reversibility tells me that for a reversible reaction, I don't have the same mechanism, so I'm going to get rid of all of this, but I do have the same intermediates. So when whoops, I didn't mean to get rid of that. And we're going to turn these arrows around. So the reaction that I'm looking at going in question number 2 is the reverse of that. And I have the exact same intermediate. So I just took that previous question in question number 1, flipped it around horizontally, and now I'm looking from left to right. And now you should ask yourself, well, what mechanistic arrows would I need to show in order to follow this intermediate pathway? And this is a review of the E1 mechanism that we saw in the previous lessons. So I'm reacting this alcohol with sulfuric acid. The laziest possible correct way of showing sulfuric acid is like this. I need lone pairs though. Again, the problem that is common is students will directly connect the hydrogen to the sulfur, and that's wrong. The hydrogen is actually connected to the oxygen. So I'm going to go over and pick up that hydrogen, and this takes me right to this compound. Okay? I actually don't need to show this hydrogen. That is a relic of when I was thinking about the reverse reactions. I'm going to delete that for the sake of simplicity. We'll space that out just a little more. Okay, first step is protonation of the alcohol. Second step is loss of water as a leaving group. Third step is the Zaitsev elimination. Whoops, got to put a hydrogen on here. Zaitsev's rule is what you think about when you're making an alkene. Markovnikov's rule is what you think about when you're breaking an alkene. So this is a review of an E1 mechanism where we made an alkene. So that's why I brought up the concept of Zaitsev's rule, where I would pull the hydrogen from the carbon with the fewest number of hydrogens. In this case, both of the beta hydrogens have 3 hydrogens. Sorry, both of the beta carbons have 3 hydrogens, so I really didn't even need to invoke Zaitsev's rule. It's just, I can't help but think about it. Okay, so that I'm going to pull the carbon, the hydrogen off of this beta. So this is my alpha carbon where the carbocation is. This is the beta carbon. I pulled the hydrogen off the beta carbon and the pi electrons from that beta hydrogen will swing down right here and form the alkene. So this right here represents the mechanism for the reverse reaction. Let's go back to right here. So this is the forward reaction. I'm going to move this in just a second, but just to prove my point, here is what we're looking. This is the new reaction, the hydration of an alkene, where we start with the alkene and end with 2-propanol. In the previous chapters, we looked at the dehydration of an alcohol to form the alkene. And these intermediates are the same going either direction. I just have to change up the arrows. So I'm going to move that back down where it goes. Show the mechanism and the corresponding energy diagram. So let's come up with an energy diagram for this reaction. Here's our axes. And we'll have energy on the y-axis and reaction progress. On the x-axis, in my energy diagram, I'm going to have 1, 2, 3 humps. The first step is just acid-base chemistry, so that's just a little jog downhill. The second step is the loss of water as a leaving group, so that's the large uphill climb to get to the carbocation. And the last step is where we get rid of the carbocation during the elimination step right here and end up at some lower energy spot overall. So there's my energy diagram for that one. Oh, I copied and pasted in the wrong place. I guess it doesn't really matter. So how does this reaction illustrate the principle of microscopic reversibility? In a reversible process, the intermediates are the same in either direction. How is the reaction manipulated to produce the desired equilibrium? So left to right, where we took an alcohol and added it to sulfuric acid, this is what we did in the DUI table. Right to left is where you're adding a water in the presence of sulfuric acid to an alkene to generate the Markovnikov alcohol. That's what we're doing today. And water here is the easiest thing to manipulate. Le Chatelier's principle tells us that if we add water to the system, it's going to push the equilibrium to the left. If we don't add water or remove water from the system, that'll push the equilibrium to the right. So one part of this that I should probably change, it says for the reaction of 2-propanol with diluted H2SO4, and the truth is if it's diluted, that means there's a bunch of water. And if you add a bunch of water to the system, the 2-propanol is really not going to react very effectively. And so I should change this question, which is what it will read on the document that I'll post for you guys, is concentrated H2SO4. Because diluted H2SO4 would not produce a large quantity of product. So that was a stupid question that I asked originally. Alright, so what have we learned to do so far today? Well, we learned how to convert an alkene into an alcohol, and that alcohol ended up at the Markovnikov, or the more substituted position of the alkene. The next thing we want to look at is how do you turn an alkene into an alcohol, but control the alcohol so that it ends up at the anti-Markovnikov position. And then this via syn addition is an issue with ring systems. So this second type of reaction we're looking at right here, the hydroboration-oxidation, would allow us to take this alkene and instead of making 2-propanol, we would make 1-propanol. And you might ask yourself, well, who cares? Well, 2-propanol and 1-propanol have different properties. They are useful in different ways. And while neither of them are pharmaceuticals, the idea of controlling the specific position upon which you dump the alcohol is a huge deal. Biology cares where the alcohol is. And if you, as an organic chemist, are trying to produce a pharmaceutical, you've got to build the alcohol in the right place. So this allows us the control. Which side of the double bond do we need the alcohol? If it's the more substituted side, then we use this top reaction. If it's the less substituted side, then we can try this bottom reaction right here. Alright, so the first question that we're supposed to answer is, show a complete reaction scheme for the entire reaction of the hydroboration-oxidation of 1-methylcyclopentene. Notice that I have an alkene, that's what I'm starting with right here, and I'm turning it into an alcohol. So that is, hopefully you recognize, the recurring theme of today's lesson. Also notice that on this alkene, this side of the alkene right here has 2 carbons, and this side of the alkene just has 1 carbon. Therefore, this side over here on the top left, is the more substituted side. And if I just use aqueous sulfuric acid, that's where the alcohol would end up. But in this product, the alcohol ends up at the anti-Markovnikov, or less substituted position. The syn addition tells me, and this really only applies to ring systems where you don't see they can't undergo free rotation, that in the hydration means I'm adding a water across the alkene, and water contains a hydrogen, an oxygen, and a hydrogen. So this is my water split across that alkene. Both the hydrogen and the OH group end up being added to the same face of the molecule. The reagents that we use in this reaction and the numbers here are a big deal. The numbers tell us that I am adding one set of reagents and then I'm adding another set of reagents. So imagine that these were cooking instructions and it tells you to, let's see, you're going to, oh, I need a better cooking analogy. I paused the video to think of one. Here's the analogy. Let's say that you're making somebody a birthday cake. You have no idea. You've never seen a birthday cake before. Somebody tells you, bake a cake and then add candles to it and then light the candles. And you don't know that those are separate steps. So you bake the cake while the candles are on it, while trying to light the candles. And that would create a mess. And so we need to specify in that first you bake the cake, and then you insert the candles. Well, then you frost it and cool it. Well, you cool it and then frost it, and then I've made cakes before, but it's been a while. So you bake the cake, then you cool it, then you frost it, then you put the candles on, then you light the candles. And the order really matters in that. If you mess up that order, you're going to have an interesting birthday party. So this right here, the one tells me that first I have to add these chemicals and I have to let them do their job. And then I clean up whatever that made, wash it, filter it, and then I add the second batch of chemicals. And that's usually a big deal when the second batch of chemicals will actually go back and react with the first batch of chemicals, which they would. This hydroxide right here would actually react with the BH3, and so you need to keep them separate. So the numbers are important, and this is why we refer to this as a two-part reaction scheme. The next question asks us about something called diglyme. Now, the diglyme is a longer name. It's an abbreviated name for diethylene glycol dimethyl ether, and it also does the same thing that THF does. So I'll kind of talk about both of these at the same time by first identifying the true behavior of BH3. BH3, because it is electron deficient, boron's weird. It tends to adopt this sextet, meaning that it only has 6 valence electrons. This BH3 molecule will actually dimerize in a way that really isn't explained well by Lewis structures. And when we look at the mechanism of this, you're going to see that boron really is not well behaved. And Lewis theory has a hard time drawing reasonable mechanisms for boron-containing compounds. But the two BH3s kind of stick together, and they end up making a compound that is best described as B2H6. And when you talk to a chemist about borane, this is probably what they're thinking of, B2H6, this dimerized mess. And so one of the things you can do is introduce an ether. So an ether, this is a particular ether called tetrahydrofuran. The ether will actually unpackage this compound, and it's essentially one of the oxygen's lone pair of electrons will stick to that boron. It's not doing it. No, let's try that. Nope, a little better. The THF, which is called tetrahydrofuran, will stick to that boron like this, and that tends to clip it apart. And so then the THF holds the BH3 kind of like a hot potato. And the bonding interaction that you get out of that kind of helps you see why it's a bit of a hot potato. The oxygen is now trying to form a covalent bond with the boron, and the oxygen in this covalent bond takes on a positive formal charge, which is a very weird and unique formal charge to see on an oxygen. And the boron, whose electronegativity is one of the lowest of any of the metalloids, takes on a negative formal charge. So it's a really low electronegative atom. This is a weird pairing, and the oxygen is happy to just take these electrons back and dump the BH3. And so this particular structure is written as BH3-THF, and that's what I have written right up here in the mechanism, or sorry, in the reaction scheme is BH3-THF, and this is kind of what that structure looks like. Diglyme is a polyether, so and I never remember the structure of it because it doesn't really matter. But let's go ahead and copy and I'll just take the structure right here, and I'll convert that into a Lewis structure so that you can appreciate what a mess it is. but also at the same time it's not that different from THF. So, no, wrong keystroke commands. This gives us a name. That name is different than the one I showed before because this is the systematic name. And this right here is the structure of diaglyne. And notice it's just a polyether. And so instead of grabbing a hold of one BH3, it grabs a hold of some number of BH3s and just kind of sticks to them. And holds them, again, like a hot potato, ready for the BH3 to do the chemistry. So when I show you the mechanism for this reaction, we just start right from the BH3 and pick up with our story as if the BH3 had already been rejected by the ether. But when we show the reagents that we have to add to make this reaction work, in the first step you add either BH3-THF, or in the first step you're going to add, they call this B2H6 and comma diaglyne. You're welcome to write down whichever one you want in a write-on type question. In an exam, or if I were asking a question, you should recognize either one of them when you see them. So those are the two different ways that we can introduce BH3 into a reaction. And so why does THF work just like diaglyne? Well, they're both ethers. So I had a little typo there, I'll fix that, and then we'll see what it looks like in the mechanism. So the last thing we need to do is come up with the mechanism for this process, and it has two parts. The first part, where you're just adding in the BH3, is a two-step mechanism, and the second part is a four-step mechanism. Okay, this is a weird mechanism. And the reason it's weird is, again, because boron does this weird thing where it kind of shares bonds in ways that other atoms simply won't. And this is not something that Lewis theory allows us to describe very well. So the first step in this hydroboration process, so the first reaction is called hydroboration and the second one is called oxidation. And the result of both steps is we end up with an anti-Markovnikov alcohol. So in the first step of the mechanism, the pi system pushes out into a boron. This is the electrophilic addition arrow that we've seen over and over again. So the pi bond reaches out, and it doesn't quite make a carbocation. Because when the pi bond pushes out, it forms a type of bond that is unique to boron. It is a 2-electron, 3-center bond. That's what the bond is called, 2-electron, 3-center, or 3-atom bond. Normally we think about a bond as 2 electrons that are shared between 2 atoms. There's a boron and a hydrogen, and they have 2 electrons. Standard 2-electron, 2-center, or 2-atom bond. When this pi bond reaches out, it doesn't actually leave the pi bond. It just kind of leans into the boron. And now these dashed lines represent the path of those 2 electrons being shared across both carbons and the boron. And this is weird. But it does actually accomplish something that you're going to start to see these reactions do. They don't actually form a carbocation. Carbocations are very unstable. Electrophilic aromatic electrophilic addition reactions have a tendency of forming carbocations. But the boron, by participating in this 2-electron, 3-center bond, skips that carbocation step. So again, this is weird. This is the only time we see this. This doesn't happen elsewhere. It's a unique feature of boron to form kind of these dashed lines right here. When it does that, there actually is a buildup of positive charge that shows up at this position. And also that methyl group kind of sterically pushes the boron away. And so in order to kind of relieve some of that steric strain and fill in the carbocation, one of the hydrides on the boron slides over in the second step, and that undoes, kind of like releases that 2-electron, 3-center bond, and now we have more classic characteristic 2 electrons for 2 atoms. But because of the triangle and that hydride shift, what ends up happening is both the boron and the hydrogen end up being added to the same face of your original pi bond. This is where the syn addition shows up, and it's also where we pushed this boron over here to the anti-Markovnikov position of the alkene. So both of the features that are kind of weird about hydroboration-oxidation reactions occur during that hydroboration step. It's a syn addition where both things are added to the same face of the pi bond, and the boron ends up on the less substituted position, the anti-Markovnikov position. Now, this reaction represents the first time that we've kind of stopped you halfway through and then introduced a second number. And what that means is, in the reaction container that you're running this, you've added the BH3, and then it'll just kind of stall out right here until you clean this up, filter it, and then apply, and then put it in a new solution full of hydroxide and hydrogen peroxide. And so you can kind of just wait here until you're ready, then you pull this out of solution and then dunk it in a brand new solution. Here in ChemDraw, I'm just going to run those two reactions together. The two steps, shown in blue, that represent hydroboration, and then the 4 steps, there's 1, and then 2, and 3, and 4 here, are going to represent the oxidation steps. When showing a mechanism, we don't often differentiate between where one reaction stops, which was here, and the next reaction starts. We just keep rolling right through our mechanism. And we assume that the person looking at our mechanism realizes, oh wait, there's some new chemical here, so this must suggest that they're identifying a different type of reaction conditions. This right here is a molecule called an ion called hydroperoxide. And if you'll notice, what I said that I added to the reaction flask was H2O2 and hydroxide, but they will react without any organic chemistry. The hydroxide just rips one of the hydrogens off of hydrogen peroxide, and we end up with hydroperoxide, and this is a pretty potent nucleophile. This hydroperoxide will push into the boron, and in doing so, it ends up giving the boron a negative formal charge. Now, this particular intermediate has all kinds of stability issues. The two main factors that drive its stability, I'm going to erase these arrows so that you just focus on the train wreck that this molecule is that generally speaking, when you have a negative formal charge, it needs to end up on the most electronegative atom. In this case, the least electronegative atom has a negative formal charge, so that's a point of instability. And the second issue is 2 oxygens singly bound to each other are just a mess. They're both very electronegative, they're kind of prickly personalities, and they will push away from each other. And we will see this feature again in other peroxide-containing compounds. It's a pretty useful reagent for organic chemists because in the peroxide bond, the OH group has a tendency to leave. When it does that, as that arrow starts to pull, imagine it stretching like a rubber band, this oxygen becomes increasingly more desperate because it's about to lose its octet. We've seen carbon without an octet. That's a carbocation. It's highly reactive. But carbon can handle a carbocation because, well, it's not that electronegative. Oxygen does not handle a cation. And so what it does is it actually reaches across the boron, grabs this pair of electrons, and slides it over simultaneously. That process, if we try to describe what's going on, I'm going to kind of cut this molecule up. It all happens simultaneously. So what I'm about to show you is kind of a pretend version of this. So let's assume that it happens in steps. And the first thing that happens is these electrons leave with the hydroxide, and this thing is just gone. And this oxygen right here did not get a hydrogen. And in fact, it's an oxygen that has a sextet, meaning only 6 total electrons, and that would give it 1, 2, 3, 4, 5. That would give it a positive formal charge. Now, it doesn't actually happen stepwise like this, but this oxygen right here has just all kinds of problems. And so what this oxygen does is it reaches over and grabs that bond. It essentially disconnects this bond from the boron entirely. I'm going to give that boron just a B. And then flips itself around. It just flips horizontally. And then reconnects that bond without changing the chiral center. Let's get rid now, and that gets rid of the positive charge here and the negative charge right there. And that's what I tried to show. That's what these 2 arrows right here, this arrow and that arrow, kind of show what I tried to show that in stop motion animation. And this is this compound right here. So this is what's referred to as a bond migration. And it's really quite rude. It's you reaching across your sibling at the dinner table and grabbing something that is on the other side of them and just pulling it right across their face. And that's what the oxygen does. The cool part about this is it solves all the big stability issues. The negative formal charge is now in this hydroxide, and we got rid of that oxygen-oxygen bond. The hydroxide, split second after it leaves, it turns around and hits that bromine in the back of the head. This is its kind of a standard SN2 reaction. pops this oxygen loose, and then it gets protonated, and then we're to the final product. So that's the 1, 2, 3, 4 steps, and it's this bond migration step that you need to practice a few times because this is unique to hydroboration. And what's cool about it is that we're able to deconstruct this oxygen peroxide bond while not messing around with the stereochemistry of this carbon over here. As far as the last step, what this oxide ion uses as a source of hydrogens to get to your final alcohol, you're going to have to protonate this to get an alcohol, and that's the product because we said so at the very beginning. So you need that. And what you choose here, it could be a water. I liked to use hydrogen peroxide here so that I kind of pay it forward, so that this peroxide ion that breaks off is the same thing and ready to start the next round of chemistry. So this kind of gives me a sense of closure with this particular mechanism. Alright, so this whole mechanism right here represents 6 total steps. This is a unique and challenging mechanism to remember, but if you break it up into the first 2 steps that involve the boron doing some weird stuff, and then the next 4 steps which involve the boron doing some weird stuff again, then hopefully that's a little easier for you to remember.